Hello everyone, here we are with another problem. This is problem 11 from chapter 7 of Introduction to Statistical Mechanics by Roger Bowley. Let's see the problem statement and then we'll dive into the solution. We have already uploaded other solutions as well. If you are interested, go visit the playlist named as Statistical Mechanics. You will find other problems there from other chapters as well. So here we can see the problem 11. It says calculate the partition function in 3 dimensions for a particle whose energy varies with wave vector as E of k equals alpha k cube. Okay, as you can see here, we need to find out the partition function for a system which is in 3D. Okay, and its energy expression in terms of wave vector is given. So using this information, we have to calculate the partition function for that system. Now let's see how we can do that. First of all, we need to mention the formula for partition function, and then we'll see what substitutions needs to be made, and we'll proceed after that. So the first thing we will do in solution is, we know that the partition function is given by z equals integral runs from 0 to infinity d of k dk e to the power minus e of k by kbt. Okay, this is the simple integral. We'll call it as equation number 1. We have used this equation to find out the partition function for different configurations, including 3D, 2D, 1D, free particles, relativistic particles, or anything else. So if you are given with density of states, the dimensions of the system, as well as its energy expression in terms of k vector and something like that, then you can totally use this formula easily to find out the partition function. And this is the general formula. You can use it for any case, even if it is 3D, 2D, or 1D. The formula remains the same for partition function. Now here we can see that there are some unknowns that we should know first before plugging the values, and these are d of k, which is density of states for the system. And we know that in 3D, since the system is 3D, density of states in k space is always given by vk square by 2 pi square. Okay, this is a general formula and it's applicable in any case you are given with. So yes, we'll use this formula. Okay, we know that for a 1D system it is L by pi, and maybe for a 2D system it is AK by 2 pi, maybe, because I don't remember actually the formula, but there are some well-defined formulas, general formulas that you people will be using any time when you are when you are going to put the density of states. So if it is a 3D system, you'll use this formula where V is the volume, K is the wave vector, and we have already done many other problems where we use these formulas and practice them so that people get familiar with these formulas. Yes, in 2D it's AK by 2 pi, in 1D it's L by pi, and in 3D it is VK square by 2 pi square. So you have to just remember these, or maybe you are given with these formulas in paper, so it's totally optional. Yeah, this is the formula that will plug right into this equation. And besides that, we also know the energy expression that is given in the question. It's alpha k cube. Let's plug these values right into equation number 1 and solve the integral in order to get the partition function. So z is equals to 0 to infinity d of k is v k square by 2 pi square. V is constant, dk is simply the part of integral, which shows that integration occurs with respect to k, and minus e of k, it is alpha k cube divided by kbt. Be mindful of the difference between k and kb. Kb is Boltzmann constant, and k is simply a variable called as wave vector. And now let me put these constants outside of integral that could be moved, and these are v by 2y square, so I'm moving them outside the integral. And now let's see how to integrate this integral. That's the crucial part to understand, because this integration is super easy if you understand how to integrate exponential functions. Before that problem, we have done other integrations where there was a where there was k to the power 1 here, okay, and something right here. So we used integration by parts, but if we use integration by parts here, it's not easy, okay. We don't need that as well, because if you understand how to integrate exponential functions, then you can easily integrate them. I have also uploaded a video where I have demonstrated a general method to integrate exponential functions, which method is used when, and many of the students are not familiar with general approaches towards integration or other things related to mathematics, because we as the new students who are firstly getting to know integration and derivations, we are normally taught about the formulas which are not general. They are true in some specific cases, and mostly we deal with those specific cases. But as you go deeper into the subject, you come to know about some of the tough integrations that requires the general understanding, the fundamental understanding that is lacking otherwise if you don't understand those general methods. So I uploaded a video where I made a complete description of how to use what method to use to integrate exponential functions. So it's up to you if you want to watch them, or you can skip that part where I'm just giving you some extra information if it's not relevant to you. Now here the derivative of the general rule is, I'll tell you people, that if you have an exponential function minus some power, let me call it p as some power, and you are integrating it, then the integration of this function, this imaginary function, is equals to that exponential function, okay, if and only if the derivative of its power comes side by side to it inside the integral, okay. If the derivative of power of exponential function comes besides the exponential function inside the integral, then that whole integral could be written as equals to that exponential function itself. So the integration would be that exponential function itself if the derivative of its power is here accompanied by the exponential function. So let's see what the situation looks like. Here we have that exponential function, okay. Now let's see what is the derivative of its power, then we'll see whether that derivative of its power could be formed here, could be adjusted to form here, so that we can write its integration to be simply equals to that exponential function. That is something that I told you people here. So let's first find out the derivative of its power in side work, so that we may know this is power including the negative sign, okay. So we'll derivate it with respect to k, because k is the main variable. Here alpha by kbt are constants, so they will come out of the derivative, and derivative of k cube is 3k square, okay. So all in all we have minus 3 alpha, I'm writing 3 here, by kbt k square. This is the derivative of its power, okay. Let's see if the derivative would be formed inside the integral, so that we may use that rule to write the integration of that exponential function that we have here. So we can see here that k square, which is variable, is already there. We just need to have this constant quantity inside the integral, and that's super easy to do because we can multiply and divide constants inside and outside of the integral. That's allowed, but we cannot do it for variables. Okay, so what we'll do is to divide this constant outside the integral and multiply this constant inside the integral, so that we may get what we want. It's minus 3 alpha by kbt outside the integral in 0 to infinity, minus 3 alpha by kbt inside the integral, and k square is already there. That's a good thing, kbt dk. So now we can write the integration of this thing to be equals to the exponential function itself, because the derivative of its power is accompanied by the exponential function inside the integral. So now we can write it equals to v by 2 pi square dot this negative sign, I'm writing it right here, and this kbt, which is in denominator of a denominator, will come in numerator. So we have v kbt divided by 3 alpha and negative sign here, and the integration here is e to the power minus alpha k cube by kbt. This is the integration, and limits of integration are 0 to infinity. Okay, let us simplify it further. Minus v kbt divided by 3 to the 6 pi square alpha. Now we'll put the limit of integration. It's we'll put these values in place of k here. So it's e to the power minus infinity, simply because infinity will multiply with the whole quantity to make it infinity. Negative sign cannot be omitted, it will be written right as it is, and in place of k we'll write 0, and 0 will multiply with the whole quantity to make it 0. With 0 plus and negative sign is irrelevant to mention, that is why I have not mentioned it here. So e to the power minus infinity is 0. Okay, from the fact that e to the power minus infinity could be written as 1 over e to the power infinity, because it's negative in the power. So to make the power positive, we'll take it in denominator, and e to the power infinity is infinity, 1 over infinity is 0. That is how I wrote e to the power minus infinity to be equal to 0. Minus e to the power 0 is 1. So 0 minus 1 is minus 1, and that minus 1 multiplies with this minus sign. Okay, 6 alpha pi square into minus 1 minus, so it makes plus, and the answer is, here I'm writing the answer, z equals v kbt by 6 alpha pi squared. Okay, this is the answer, this is the final answer. I hope you people understood it, and I'll meet you in next video.